Golden Gate Bridge. Since 1937, this iconic suspension bridge has stood as a testament to human engineering, spanning the Golden Gate Strait with 80,000 miles of steel cable. But what makes these twisted strands of steel capable of bearing such extraordinary weight? The answer lies in a manufacturing process that transforms raw iron ore into one of the strongest materials used in modern construction. From the mines to the steel mill, every step is designed to create cables that are not just strong, but resilient enough to withstand decades of stress, weather, and constant use. This is the story of steel cable manufacturing that combines metallurgy, precision engineering, and quality control to produce a material that quite literally holds our modern world together. Welcome to Mighty Machines. In the early 1800s, the mining industry faced a critical limitation. Hemp ropes, which had been used for centuries, simply couldn't handle the increasing depths and loads required by expanding mining operations. These natural fiber ropes would fray, rot, and fail under extreme tension. The solution came in the 1830s from the mining regions of Germany. Wilhelm Albert, a mining engineer, developed the first wire rope by twisting individual steel wires together. This innovation changed everything. Mine hoists could now descend hundreds of meters safely, opening up previously inaccessible mineral deposits and accelerating the Industrial Revolution. Today, nearly 2 centuries later, the global steel wire rope industry produces over 10 million tons annually. These cables are everywhere, managing containers at ports, suspending bridges across vast spans, supporting oil rigs, and lifting the heaviest objects mankind has ever made. The basic principle remains the same. Individual steel wires, each relatively thin, gain extraordinary strength when twisted together in precise configurations. What makes this particularly remarkable is the efficiency of the design. A steel cable just 5 centimeters in diameter can support loads exceeding 200 tons. This isn't magic, it's engineering. The helical structure distributes tensile forces evenly across all the wires, while the twisting pattern allows the cable to bend and flex without breaking. It's a perfect marriage of strength and flexibility. Every steel cable begins its life as iron ore, buried deep within the earth. Modern iron ore mining is a carefully orchestrated operation involving some of the largest machines ever built. The process starts with geological surveys that identify ore deposits. Once a viable site is confirmed, mining operations begin with drilling. Massive rotary drill rigs, some standing over 15 meters tall, bore precisely spaced holes into the rock face. These aren't random. The drilling pattern is calculated to ensure optimal fragmentation during blasting. The holes are then loaded with carefully measured amounts of explosives. When detonated in sequence, these controlled blasts fracture millions of tons of rock, exposing the iron ore within. The reddish-brown color you see in iron ore comes from iron oxide, essentially rust, which makes up 60 to 70% of the raw material. Now the real heavy lifting begins. Electric rope shovels and hydraulic excavators, some with bucket capacities exceeding 50 cubic meters, load the blasted ore onto haul trucks. These aren't ordinary trucks. Ultra-class mining trucks can carry payloads of 400 tons or more, and their diesel engines produce over 3,000 horsepower just to move these massive loads up steep haul roads. At the processing facility, the ore undergoes primary crushing and screening. Vibrating screens separate different size fractions, while magnetic separators remove unwanted rock. This pre-processed ore is then loaded onto dedicated rail cars or massive bulk carrier ships. A single ore carrier can transport 200,000 tons in a single voyage, making the journey from mine to mill an exercise in logistics as much as mining. Modern steelmaking uses electric arc furnaces, massive vessels that can hold 150 tons or more of raw material. The furnace is loaded with iron ore, recycled steel scrap, and flux materials. Then, 3 graphite electrodes, each nearly a meter in diameter, are lowered into the furnace. When energized, these electrodes draw an electric arc that generates temperatures exceeding 3,000 degrees Celsius. At this temperature, solid metal becomes a glowing, churning liquid. But creating steel isn't just about melting iron. It's about controlling chemistry at an industrial scale. For cable manufacturing, the steel needs specific properties: high tensile strength, good ductility, and resistance to fatigue. This is achieved through alloying. Manganese is added to increase strength and hardness. Depending on the application, the steel might contain 0.6 to 1.5% manganese. Silicon improves the steel's ability to be drawn into wire without cracking. Chromium might be added for corrosion resistance in marine applications. Meanwhile, impurities need to be removed. Quicklime and fluorspar are added to form slag, a lighter molten material that floats on top of the steel, absorbing sulfur, phosphorus, and other unwanted elements. This slag is continuously skimmed off, leaving progressively purer steel below. Throughout this process, automated sampling systems extract small amounts of molten steel for analysis. Spectrometers provide real-time chemical composition data, allowing operators to make adjustments within minutes. This level of control ensures consistency, critical when the final product needs to meet strict engineering specifications. Once the steel chemistry is correct, the molten metal moves to the continuous casting machine. This is where modern steelmaking shows its efficiency. Continuous casting replaced the old ingot method, where steel was poured into individual molds and allowed to cool completely. Instead, molten steel flows continuously into a water-cooled copper mold. The copper conducts heat rapidly, so the outer shell of steel solidifies almost instantly upon contact. As the solidified shell moves downward, the liquid core slowly freezes from the outside in. The casting machine carefully controls this cooling rate because it affects the internal structure of the steel. The result is a continuous strand of solid steel that emerges from the bottom of the caster. Automated torches cut this strand into billets, typically 6 to 12 meters long, with a square cross-section of 150 to 200 millimeters. These billets are still glowing red-hot, typically around 1,000 degrees Celsius. Rather than letting this heat go to waste, they're sent immediately to the rolling mill, while still hot and malleable. The rolling mill is where brute force meets precision. Massive steel rollers, some weighing 50 tons each, are arranged in a series of stands. Each stand applies several thousand tons of force, squeezing and elongating the billet. As the billet passes through the first stand, it's compressed and stretched. Then it enters the next stand, where the rollers are set slightly closer together. With each pass, the cross-section decreases and the length increases. A 6-meter billet might be stretched to 60 meters or more by the time it exits the final stand. This isn't just about changing shape. The mechanical working at high temperature refines the internal grain structure. The large irregular grains in the cast billet are broken down and reorganized into a finer, more uniform structure. This dramatically improves the steel's mechanical properties, its strength, toughness, and ability to be drawn into wire. Temperature control is critical here. If the steel cools too much during rolling, it becomes harder to deform and might crack. Rolling mills use induction heaters between stands to maintain temperature, and computer systems monitor the exact temperature of the steel at multiple points along the line. After hot rolling produces round bars or rods, the steel is cooled and prepared for wire drawing. This is where the real precision begins. Wire drawing works on a simple principle. Pull steel through a die with a hole slightly smaller than the wire's current diameter. The steel is forced through, becoming thinner and longer in the process. But executing this simple principle at industrial scale requires sophisticated engineering. First, the steel passes through a series of rolling stands at room temperature. Each stand reduces the diameter slightly and improves the surface finish. The steel emerges as wire rod, typically 5 to 12 millimeters in diameter. Then comes wire drawing. Modern drawing machines might have 10 to 20 dies in sequence, each reducing the diameter by about 15 to 25%. The friction between steel and die generates significant heat, so the process uses lubricants, specialized drawing compounds that reduce friction and cool the wire. In high-speed operations, the wire might be moving at 20 meters per second or faster. Precision is measured in micrometers. The result is wire with diameter variations of less than 0.01 millimeters, critical for the cable's final properties. Steel's greatest weakness is corrosion. Even small amounts of rust can significantly reduce a cable's strength over time. Protective coatings solve this problem. The most common coating is galvanization, applying a layer of zinc. The wire first passes through a cleaning bath that removes any residual oil or oxide. Then it's immersed in molten zinc at around 450 degrees Celsius. The zinc doesn't just coat the surface, it actually bonds metallurgically with the steel, forming a series of zinc-iron alloy layers. When the wire emerges and cools, it has a bright, silvery appearance and a protective layer that can last for decades, even in harsh environments. For specialized applications, polymer coatings might be used instead. These are applied either by extrusion or powder coating, creating a thick barrier that protects against particularly aggressive chemical environments. Modern coating lines use X-ray fluorescent sensors to measure coating thickness in real time, maintaining tolerances of just a few micrometers. Before wire can be approved for cable manufacturing, it must pass rigorous inspection. Automated systems check every meter of wire as it's produced. Optical systems scan for surface defects, scratches, pits, or coating inconsistencies. Eddy current sensors detect internal flaws that aren't visible to the eye. Laser micrometers confirm the diameter is within specification. Sample sections are pulled off the line regularly for destructive testing. Tensile testing machines pull the wire until it breaks, measuring its ultimate strength and elongation. The results must fall within a narrow range. Typically, the wire must achieve at least 95% of the theoretical strength for its size and grade. Any wire that fails inspection is immediately segregated. In quality manufacturing, there's no second chance. It's either right or it's scrapped and remelted. This is where individual wires become a cable. The stranding machine is a marvel of mechanical engineering. A massive rotating frame that holds dozens or even hundreds of wire spools. The basic structure of most cables follows a pattern. A central core surrounded by layers of wires twisted in a helix. A simple cable might have a 7-wire construction. One center wire with 6 wires twisted around it. Complex cables can have multiple layers with hundreds of individual wires. The core can be steel for maximum strength or fiber for lighter weight and better resistance to crushing. As the stranding machine rotates, it pulls wires from the outer spools and twists them around the core at a precisely controlled angle, typically between 10 and 25 degrees. Modern stranding machines use servo motors to adjust individual wire tensions thousands of times per second. Layer by layer, the cable is built up. Outer layers might be twisted in the opposite direction to inner. This creates a balanced cable that won't untwist under load. The entire process is computer-controlled, ensuring every meter of cable has identical construction. A cable fresh from stranding might look complete, but it's not ready for service. The tight contact between wires creates friction during use, which causes wear. Lubrication solves this problem. The cable passes through a lubrication system that forces oil into the spaces between wires. This isn't ordinary oil, it's specially formulated for the application. It also protects against moisture penetration, keeping the interior wires as corrosion-free as the exterior. Before a cable leaves the factory, it must prove itself. Sample lengths are subjected to destructive testing that simulates years of service in hours. Breaking strength tests pull the cable until it fails, confirming it exceeds the rated capacity. Fatigue testing flexes the cable back and forth thousands of times under load, simulating years of elevator service. Electromagnetic sensors detect wire breaks inside the cable that aren't visible externally. Diameter measurements confirm consistency along the entire length. Only cables that pass every test receive certification. Approved cables are wound onto massive reels, some weighing several tons when full. The winding process itself requires precision. The reels are wrapped in protective covering and marked with identification data. Then they're loaded onto trucks or shipping containers for delivery to customers around the world. From iron ore to finished cable, the process takes weeks and involves dozens of individual steps. But the result is a product that can last for decades, supporting loads measured in hundreds of tons, working reliably in conditions from Arctic cold to tropical heat. Steel cable might look simple, just twisted wires. But as we've seen, creating a cable that can safely support a bridge, lift an elevator, or secure an offshore platform requires precision at every step. It's a combination of metallurgy, mechanical engineering, and quality control, all working together to create one of the strongest materials in use today. This is the kind of engineering that makes modern life possible. And here at Mighty Machines, this is the kind of process we love to explore. If you enjoyed this look inside steel cable manufacturing, make sure you're subscribed so you don't miss our next deep dive into the machines and processes that build our world.